The cosmos harbors countless threats to our fragile existence, but few inspire the primal terror quite like black holes. The mere thought of one materializing without warning, pulling Earth into an inescapable gravitational embrace, haunts the imagination. It's the kind of catastrophe that keeps theoretical physicists awake at night, not because it's likely, but because once it began, there would be absolutely nothing we could do to reverse it. No technology, no strategy, no amount of human ingenuity could halt the inexorable collapse. Imagine the scenario unfolding in slow motion. The growing void would consume everything in its path, pulling matter into itself with escalating hunger. Buildings, mountains, oceans, all would spiral inward, compressed beyond recognition. In time, every trace of human civilization would be wiped from existence, erased as thoroughly as if we'd never been here at all. All that would remain would be a handful of spacecraft and space debris, lonely artifacts drifting through the emptiness of our solar system, silent witnesses to a species that once looked up at the stars and dared to ask questions. This sounds like science fiction, the plot of a summer blockbuster where humanity faces its ultimate reckoning. But here's the unsettling reality. In 2008, the European Organization for Nuclear Research, better known by its French acronym, CERN, activated a machine that they acknowledged had a non-zero probability of creating a black hole right here on Earth. Not in some distant galaxy, not in the far future. Here, now, on our planet. The encouraging news is that we're all still here. We haven't been devoured by an all-consuming gravitational maw. The Earth continues its orbit, life persists, and civilization carries on. But here's what should give you pause. CERN's official documentation actually states that their machine, the Large Hadron Collider, could still create a black hole. That possibility hasn't been ruled out. It remains on the table as a potential outcome of their ongoing experiments. So have we simply been fortunate up to this point? Have we been rolling the dice with our planet's survival and just happening to win each time? And what are the genuine risks if we continue pushing the boundaries of particle physics in the name of scientific advancement? What happens if our luck runs out? Today, we're going to explore the science behind artificial black hole creation. We'll examine the mathematical realities, the theoretical frameworks, and the actual dangers, or lack thereof, associated with humanity's most ambitious attempt to recreate the conditions of the early universe. We're going to uncover the truth about whether CERN's experiments pose an existential threat to everything we know and love. The Large Hadron Collider represents one of humanity's most ambitious engineering achievements. Picture a circular tunnel stretching 27 kilometers in circumference, buried deep beneath the border between France and Switzerland. This tunnel houses 9,593 magnets, each one precisely calibrated to guide beams of particles along their circular path. The entire apparatus is designed for one purpose: to accelerate protons and heavy ions toward each other at velocities that boggle the mind. 1% the speed of light. Let that number sink in for a moment. We're talking about particles moving so fast that the difference between their speed and the speed of light itself is almost negligible. At these velocities, the particles possess enormous kinetic energy, despite their infinitesimal mass. When they collide, that energy has to go somewhere, and according to Einstein's famous equation relating mass and energy, it can transform into new particles that didn't exist before the collision. The Large Hadron Collider generates approximately 1 billion particle collisions every single second. That's not a typo. 1 billion collisions, second after second, hour after hour, day after day. Each collision is monitored by sophisticated detectors, creating an avalanche of data that requires some of the world's most powerful computers to process. The facility consumes roughly 600 gigawatt hours of electricity per year, enough energy to power a city of over 100,000 people. That's comparable to the annual electricity consumption of a place like Green Bay, Wisconsin, or Cambridge, England. But why? Why invest billions of dollars, decades of human effort, and enough electricity to power a small city into smashing particles together? The answer is both simple and profound. Scientists use the LHC to recreate the extreme conditions that existed in the first fraction of a second after the Big Bang, but on a microscopic scale, contained and controlled within the heart of their detectors. In those first moments after the universe came into existence, temperatures and energies were so extreme that matter as we know it couldn't exist. Instead, The universe was filled with a seething soup of fundamental particles, the basic building blocks from which everything else would eventually form. By recreating those conditions, scientists can study these fundamental particles, observe how they interact, and test the theories that attempt to explain the underlying structure of reality itself. When the particles accelerated by the LHC collide head-on, their kinetic energy can be converted into mass through Einstein's mass-energy equivalence principle. This allows the creation of heavy particles that wouldn't normally exist in nature, at least not at the temperatures and pressures we experience in everyday life. These exotic particles survive for only the tiniest fractions of a second before decaying into lighter, more stable particles. But in that brief moment of existence, they can be detected, measured, and studied. Detectors surrounding the collision points record the spray of particles produced in each impact. Think of these detectors as incredibly sophisticated cameras, capable of capturing events that happen far too quickly for any human observer to perceive. By analyzing the debris from billions upon billions of collisions, scientists can work backward to determine what was created in each event, piecing together evidence for the elementary particles that make up the standard model of particle physics. The Standard Model is our best current understanding of the fundamental particles and forces that govern the universe. It describes quarks, leptons, bosons, and the forces through which they interact. But the Standard Model was built on theoretical predictions that needed experimental confirmation. And the Large Hadron Collider has been crucial in providing that confirmation. The most famous example is the Higgs boson, a particle that was predicted to exist decades before it was actually discovered. The Higgs boson is responsible for giving other particles their mass through its interaction with the Higgs field, an invisible field that permeates all of space. Without the Higgs mechanism, particles would have no mass, atoms couldn't form, and the universe as we know it couldn't exist. The Higgs boson was finally discovered at the LHC in 2012, confirming a prediction that had been made back in the 1960 seconds and earning Peter Higgs and Francois Englert the Nobel Prize in Physics. But finding fundamental particles is only part of CERN's mission. The organization hopes to answer some of the most profound questions in physics, mysteries that have puzzled scientists for decades. What is dark matter? This invisible substance makes up roughly 27% of the universe's mass-energy content. Yet we've never directly detected it. We know it exists because of its gravitational effects on visible matter, but we don't know what it's made of. Could the LHC create dark matter particles and finally reveal their nature? What about dark energy, the mysterious force causing the universe's expansion to accelerate? It accounts for about 68% of the universe's total energy, yet we understand almost nothing about it. Why is there more matter than antimatter in the universe? When matter and antimatter meet, they annihilate each other in a burst of energy. The Big Bang should have created equal amounts of both, which would have annihilated completely, leaving behind only energy. Yet here we are, living in a universe made of matter. Why didn't everything cancel out? Is there evidence for supersymmetry, a theoretical framework that predicts each known particle has a heavier superpartner? Supersymmetry could help explain dark matter and unify the fundamental forces of nature. But so far, no superpartner particles have been detected. The LHC continues to search. To put it simply, the Large Hadron Collider is one of the most powerful tools we have for investigating the deepest mysteries of existence. It allows us to probe the fundamental nature of reality, to test theories about how the universe works at its most basic level. For many in the scientific community, particularly physicists, this represents an extraordinary opportunity to expand human knowledge. But not everyone viewed the LHC's activation with enthusiasm and excitement. From the moment CERN announced the collider's capabilities, concerns began to surface. And among these concerns, one fear rose above all others, capturing headlines and sparking debates worldwide: the possibility that the Large Hadron Collider might create black holes. When this possibility was first revealed to the public, it instantly became a global news story. Media outlets around the world ran headlines asking whether CERN was about to destroy the planet. The reaction was, understandably, mixed and often heated. Some people, particularly those with backgrounds in physics, downplayed the risks. They argued that the machine was perfectly safe after all. Would thousands of the world's smartest scientists really turn on a device that posed a genuine threat to human survival? Scientists aren't suicidal. They have families, children, and a stake in humanity's future, just like everyone else. Others took the threat more seriously. Lawsuits were filed in multiple countries, attempting to legally prevent CERN from activating the LHC until more safety assessments could be conducted. These lawsuits ultimately failed, dismissed by courts that found the scientific evidence for danger to be lacking. Still, others made dark jokes about our collective impending demise, treating the whole situation with gallows humor. After all, if we were really about to be consumed by a black hole, at least we'd all go together. But not all of this worry was entirely justified, and some of the information circulating at the time was simply false. The internet, as it tends to do, amplified both legitimate concerns and complete nonsense in equal measure. Conspiracy theories spread like wildfire, particularly on social media platforms, where fact-checking was minimal and sensationalism ruled. Let's address one particular claim right now, once and for all. No, CERN is not creating a portal to hell in the Large Hadron Collider. This absurd theory circulated widely on Facebook and other platforms, accompanied by photoshopped images and breathless warnings about demonic entities. It was thoroughly debunked by fact-checkers, but it persists in certain corners of the internet to this day, demonstrating how difficult it is to kill a good conspiracy theory once it takes root. But while the portal to hell claim was easily dismissed as fanciful nonsense, the black hole concern is different. It's more resilient, harder to shake off. Why? Because according to our current understanding of physics, there actually is a chance, however small, that the LHC could create a black hole. This isn't conspiracy theory territory. This is legitimate science, acknowledged by CERN itself. So why did CERN turn on the Large Hadron Collider if there was any risk at all? Even a small probability of planetary annihilation should give us pause. Isn't the pursuit of knowledge, however noble, a little reckless when the stakes are this high? Would you flip a coin if heads meant an interesting scientific discovery but tails meant the end of all life on Earth? To answer these questions, we need to dive into the mathematics and physics of black hole formation. We need to understand what the actual risks were and are when CERN smashes particles together at near-light speeds. What was the real probability that we were about to create an apocalyptic, homemade black hole? Black holes, in theory, are remarkably simple to make. In practice, of course, it's a different story. In nature, black holes form when massive stars collapse. We're talking about stars at least 20 times more massive than our Sunday. When such a star exhausts its nuclear fuel, it can no longer support itself against its own gravity. The core collapses catastrophically in what we call a supernova, one of the most violent events in the universe. The forces involved in a supernova are almost incomprehensible. Imagine the mass of multiple suns being crushed together in a matter of seconds. The pressures become so extreme that atoms themselves are torn apart. First, electrons are forced into atomic nuclei, combining with protons to form neutrons. This creates what's called a neutron star, an object so dense that a teaspoonful of its material would weigh about 1 billion tons on Earth. But if the collapsing star is massive enough, even the neutron degeneracy pressure, the quantum mechanical principle that prevents neutrons from occupying the same space, can be overcome. And when that happens, nothing can stop the collapse. The core compresses infinitely, or at least to a point so small that it's effectively a singularity, a point of infinite density where our understanding of physics breaks down completely. Around this singularity, an event horizon forms. This is the point of no return, the boundary beyond which nothing, not matter, not energy, not even light itself can escape. Space-time is curved so severely near the event horizon that all paths lead inward. There is literally no direction you can travel that will take you away from the singularity once you've crossed that threshold. The event horizon's size depends on the black hole's mass. For a stellar mass black hole, the kind formed from a collapsing star, the event horizon might be a few kilometers across. For supermassive black holes like the one at the center of our galaxy, which contains millions or billions of solar masses, the event horizon can be larger than our solar system. Here's the interesting part. While in nature we only observe black holes forming from stars of at least 20 solar masses, there's no fundamental law of physics that says you need that much mass to create a black hole. The requirements are actually quite simple. You need to compress matter to the point where its escape velocity exceeds the speed of light. That's it. That's the only requirement. Black holes can theoretically be any size, large or small. A black hole with the mass of the Earth would have an event horizon only about 9 millimeters across, smaller than a marble. A black hole with the mass of the Sun would have an event horizon about 3 kilometers in radius. The relationship is linear. Double the mass, double the radius of the event horizon. This means that, in principle, you could create a black hole from any amount of matter, even a single proton, provided you could compress it to within its Schwarzschild radius, the radius at which that particular mass would form an event horizon. For a proton, the Schwarzschild radius is mind-bogglingly small, roughly 10 to the power of minus 54 meters. That's so small it's effectively meaningless, far smaller than anything we can measure or even meaningfully conceive of. In nature, we don't see tiny black holes, because we don't encounter the kinds of forces necessary to create them outside of sufficiently massive stellar collapses. The energies involved in everyday processes, even violent ones like nuclear explosions or meteor impacts, fall far short of what would be needed. You need truly cosmic-scale forces, but the Large Hadron Collider smashes particles together with tremendous force. These collisions are among the most energetic events humans have ever created, concentrated in an incredibly small space. So the question becomes, is the LHC capable of generating enough force to compress particles beyond their Schwarzschild radius and create a black hole? To answer this question requires some mathematics, but don't worry if numbers aren't your strong suit. The concepts themselves are straightforward enough that anyone can grasp them with a bit of patience. The impacts in the Large Hadron Collider are measured using a unit called the tera-electron-volt, abbreviated as TeV. 1 tera-electron-volt is roughly equivalent to the kinetic energy of a flying mosquito. Now, that might not sound particularly impressive at first. A mosquito? That's what all the fuss is about? But remember, and this is crucial, this energy is being delivered to individual protons. Particles so small that a single human hair is about 1,000,000 times wider than one. We're talking about packing the kinetic energy of a mosquito into a space smaller than an atom. That's a tremendous amount of energy concentrated in an almost unimaginably small volume. It's like taking a freight train traveling at highway speeds and compressing all that momentum into something the size of a grain of sand. You're getting an extraordinary amount of force for your buck. When the Large Hadron Collider first became operational, the particles were accelerated to energies of 3.5 TeV. When two such particles collided head-on, you'd get a combined impact energy of 7 TeV. That was just the beginning. The initial test runs to make sure everything worked as designed. As engineers gained confidence in the system and fine-tuned its performance, they gradually increased these energies. Over time, the collision energies were scaled up significantly. By the mid-2020 seconds, particles were being accelerated to 6.8 TeV each, producing total collision energies of 13.6 TeV. And even that represents only a fraction of CERN's ultimate ambitions. The Large Hadron Collider was never intended to be the final word in particle physics. It's just the current generation of technology. Plans are already well underway for the LHC's successor, a machine called the Future Circular Collider, or FCC. This proposed facility would dwarf the current installation. Where the LHC has a circumference of 27 kilometers, the FCC is designed to be 91 kilometers around, more than 3 times larger. The increased size would allow particles to be accelerated to far higher energies before collision. The goal for the Future Circular Collider is to achieve total collision energies of 100 TeV. Yes, that's the kinetic energy of 100 mosquitoes, all compressed into the collision point between two protons. At these energy levels, physicists hope to probe even deeper into the structure of matter, potentially discovering new particles and forces that remain hidden at lower energies. But here's the critical question. Is even 100 TeV enough energy to create a black hole? The answer, according to our current understanding of physics, is a resounding no. It's not even close. In 2010, physicists conducted detailed mathematical modeling to determine exactly how much energy would be required to smash particles together with sufficient force to compress them within their Schwarzschild radius and form a black hole. The calculations involved quantum mechanics, general relativity, and some rather sophisticated mathematics, but the conclusion was clear and unambiguous. The energy required came out to approximately 1/3 of what's called the Planck energy. The Planck energy is a fundamental value in physics, the energy scale at which our classical understanding of how matter and energy behave begins to break down. At this level, quantum effects and gravitational effects become equally important, and we enter a regime where quantum gravity A theory that successfully merges quantum mechanics with general relativity would be necessary to make predictions. The problem is that we don't yet have a working theory of quantum gravity. Despite decades of effort by some of the brightest minds in theoretical physics, nobody has successfully unified quantum mechanics and general relativity into a single coherent framework. This means that what happens at and beyond the Planck energy is something of an enigma, a frontier where our current understanding simply peters out. But here's what we do know. The Planck energy has a value of approximately 1.2 times 10 to the power of 19 GeV, or about 2 billion joules. To put that in perspective, that's roughly the energy content of 50 kilograms of TNT, or about the energy in 15 gallons of gasoline. That might not sound like an enormous amount of energy in everyday terms. A car's fuel tank holds more than that. But remember, we're talking about compressing all of that energy into a space smaller than a proton. The Large Hadron Collider, operating at its current maximum capacity of about 13.6 TeV, generates energies that are roughly a quintillion times smaller than the Planck energy. A quintillion is a 1 followed by 18 zeros. To say that the LHC isn't even in the same ballpark as the energy needed to create a black hole would be a dramatic understatement. It's not even in the same universe of possibility. Even the proposed Future Circular Collider, with its ambitious 100 TeV collision energy, would still fall short by a factor of about 100 quadrillion. You could run the FCC for the entire age of the universe so far, conducting trillions upon trillions of collisions, and never once have enough energy concentrated in one place to form a black hole, according to our standard understanding of physics. So, it sounds like we're completely safe, right? The numbers seem to indicate that there's absolutely no chance of the LHC creating a black hole. Case closed. We can all sleep soundly at night, knowing that CERN's experiments pose no threat whatsoever to our continued existence. But if that's truly the case, then why did CERN themselves acknowledge that they might create a black hole? Why did their official safety assessments include discussions of black hole formation scenarios? Why were physicists even worried about this possibility in the first place? The answer lies in the fundamental nature of reality itself, and specifically in the question of how many dimensions our universe actually contains. This is where things get genuinely weird, where we venture into territory that sounds more like science fiction than science fact. But stay with me, because understanding this is crucial to understanding the real risks, or lack thereof, associated with the Large Hadron Collider. We experience the universe as having 4 dimensions. 3 of these are spatial: forward and backward, left and right, up and down. You can move in any combination of these 3 directions to reach any point in 3-dimensional space. The 4th dimension is time, which flows in one direction, at least from our perspective, from past to future. This 4-dimensional framework, called space-time, has been the foundation of physics since Einstein formulated his theories of special and general relativity in the early 20th century. It's been tested countless times and has passed every experimental verification we've thrown at it. For all practical purposes, we can treat the universe as having 4 dimensions and make accurate predictions about how matter and energy behave. But some theoretical physicists believe that this 4-dimensional picture might be incomplete. They propose that our universe actually contains additional dimensions beyond the 4 we can perceive. These extra dimensions would be radically different from the ones we experience in everyday life. They wouldn't be large spatial dimensions you could travel through or observe directly. Instead, they would be incredibly tiny, curled up so tightly that they're effectively invisible to us. Imagine a garden hose seen from a great distance. From far away, the hose looks like a one-dimensional line. It has length, but no apparent width. But if you could zoom in close enough, you'd discover that the hose actually has 2 dimensions: length along the hose and circumference around it. An ant walking on the hose could travel in either direction. The circumference dimension was always there, but it was hidden from distant observers because it was curled up into a small circle. In a similar way, theoretical physicists propose that additional spatial dimensions might exist at every point in our universe, but curled up so tightly, perhaps at scales smaller than subatomic particles, that we can't detect them directly. From our perspective, moving through space, we only notice the 3 large dimensions. The extra dimensions are there, just hidden from view. This idea isn't just wild speculation. It emerges naturally from certain theoretical frameworks, most notably string theory. String theory attempts to unify all the fundamental forces of nature and explained the properties of all known particles by proposing that the basic building blocks of reality aren't point-like particles, but tiny vibrating strings of energy. Different vibration patterns of these strings would correspond to different particles. An electron would be a string vibrating one way. A quark would be the same string vibrating differently. String theory is mathematically elegant and has some appealing features, but it comes with a catch. The mathematics only works consistently if the universe has more than 4 dimensions. The most common version of string theory requires 10 dimensions, total 9 spatial dimensions plus time. More exotic variants, like M theory, require 11 dimensions. Now, the existence of these extra dimensions is far from proven. String theory, despite decades of development, remains largely untested. It makes few predictions that can be verified with current technology, and many physicists are skeptical about whether it describes reality or is merely an interesting mathematical construct. The existence of extra dimensions is very much an open question in physics. But here's why this matters for the Large Hadron Collider and black hole creation. If these extra dimensions exist, they fundamentally change the mathematics of gravity and energy. In a universe with only 4 dimensions, gravity behaves according to the inverse square law. Double the distance between 2 objects, and the gravitational force between them decreases by a factor of 4. This relationship emerges directly from the geometry of 3-dimensional space. But in a universe with additional spatial dimensions, gravity would spread out through more directions. It would dilute differently as you move away from a massive object. And this changes how we calculate the Planck energy, the energy scale at which quantum gravity effects become important. In certain extra-dimensional models, the Planck energy could be dramatically lower than the value calculated for a 4-dimensional universe. Some scenarios bring the effective Planck energy down by many orders of magnitude. And if the Planck energy is lower, then the energy required to create a black hole is correspondingly lower. In some of these theoretical frameworks, the energy required to form a black hole could potentially drop all the way down to the range that the Large Hadron Collider can actually achieve. The LHC would be operating right at the boundary where black hole formation becomes possible. Every collision between particles would have a tiny chance of compressing matter sufficiently to create a microscopic black hole. This is why CERN acknowledged the possibility. Not because they thought it was likely in our familiar 4-dimensional universe, but because if we happen to live in a universe with extra dimensions, and if those dimensions have the right properties, then the LHC might, just possibly, create black holes. For string theorists and physicists who believe in extra dimensions, this prospect was actually quite exciting. If the LHC created a black hole, it would be direct experimental evidence for extra dimensions. Confirmation of theoretical predictions that have been made over decades. It would revolutionize our understanding of the universe and vindicate years of theoretical work. Of course, there's a small downside. That black hole would presumably proceed to devour the planet, ending human civilization and all life on Earth. But at least the string theorists would have been proven right, even as the black hole consumed the laboratory, the cities, the continents. A consolation prize, perhaps, as everything we've ever known or loved is compressed into a singularity. Except here's the thing. Even if extra dimensions exist, and even if the LHC did create a black hole, our planet would actually survive surprisingly well. And there are multiple independent reasons why this is true, each one sufficient on its own to prevent catastrophe. The first and perhaps most important reason comes from a surprising property of black holes that was discovered relatively recently in the history of physics. For decades, scientists believed that nothing could escape from a black hole once it crossed the event horizon. The term event horizon itself reflects this. It's the horizon beyond which events become causally disconnected from the outside universe. If something crosses that boundary, it can never send information or energy back out. It's gone forever, as far as the rest of the universe is concerned. This seemed to be an inescapable consequence of general relativity. Einstein's equations describing gravity and space-time curvature appeared to lead inevitably to this conclusion. A black hole was the ultimate prison, a one-way journey to oblivion. But in 1974, a young physicist named Stephen Hawking published a paper that turned this understanding on its head. Hawking had been thinking about what happens at the event horizon when you include quantum mechanics in the picture. Quantum mechanics describes the behavior of matter and energy at very small scales, and it's full of counterintuitive effects that have no parallel in everyday experience. One of these quantum effects is the constant creation and annihilation of particle-antiparticle pairs throughout space. According to quantum field theory, empty space isn't actually empty. It's seething with virtual particles that pop into existence in pairs, exist for a brief instant, and then recombine and annihilate each other. These virtual particles are normally undetectable because they exist for such a short time and never travel far from their point of creation. But Hawking realized that something interesting happens when these virtual particle pairs appear near a black hole's event horizon. Occasionally, one particle of the pair would fall across the event horizon while its partner escaped. The particle that fell in would carry negative energy from the perspective of the black hole, effectively reducing the black hole's mass. Meanwhile, the particle that escaped would carry positive energy away from the black hole. To a distant observer, it would appear as if the black hole was emitting radiation. This radiation, now called Hawking radiation, would have a thermal spectrum corresponding to a temperature inversely proportional to the black hole's mass. Larger black holes would have lower temperatures and emit radiation more slowly. Smaller black holes would be hotter and radiate more quickly. The implications of Hawking's discovery were profound. Black holes aren't truly black, they glow, albeit very faintly in most cases. And because they emit energy in the form of radiation, they must be losing mass, according to Einstein's mass-energy equivalence. This means that all black holes will eventually evaporate completely, radiating away their entire mass over time. For large black holes, this process takes an extraordinarily long time. A stellar mass black hole, the kind formed from a collapsing star, would take far longer than the current age of the universe to evaporate through Hawking radiation. The supermassive black holes at the centers of galaxies would take even longer. Some estimates suggest they wouldn't evaporate completely until 10 to the power of 100 years have passed, a time so vast that it's essentially meaningless. But here's the crucial point. The evaporation process speeds up dramatically as the black hole gets smaller. As a black hole loses mass through Hawking radiation, its temperature increases, causing it to radiate even faster. This creates a runaway effect. The black hole radiates, gets smaller, gets hotter, radiates faster, gets smaller still, and so on, accelerating toward a final explosive endpoint. By the time a black hole is shrunk to microscopic size, the kind of size we're talking about if the LHC created one, it would be phenomenally hot and radiating energy at an enormous rate. The final moments of evaporation would release all the remaining mass energy in a burst, effectively a tiny explosion. How tiny? Let's consider a worst-case scenario where all the energy in a single LHC collision somehow ended up concentrated in a microscopic black hole. Remember, these collisions involve a total energy of about 14 trillion electron volts, or 14 TeV in the units physicists use. We can use Einstein's equation E equals mc squared to convert this energy into an equivalent mass and get a sense of scale. 14 trillion electron volts works out to approximately 2.2 times 10 to the power of minus 5 joules. That's a very small amount of energy in everyday terms. To put it in perspective, it's roughly equivalent to the kinetic energy of a tiny grain of sand, perhaps a milligram in mass, moving at about 2 meters per second. Alternatively, it's about the energy contained in a couple of flying mosquitoes, which is where that mosquito analogy from earlier comes back into play. Now, if a black hole containing this much energy were to evaporate completely through Hawking radiation, releasing all that energy at once, what would happen? Would it be a catastrophic explosion, a miniature nuclear detonation in the heart of the detector? No. The explosion would be so small you probably couldn't even detect it without sophisticated instruments. If such a black hole exploded in your hand, you might feel a tiny warmth if you were paying very close attention, but more likely you'd notice nothing at all. It would be far weaker than the static electricity shock you get from touching a doorknob on a dry day. Of course, CERN is paying very close attention to what happens in their detectors. The physicists and engineers monitoring the Large Hadron Collider have instruments sensitive enough to detect incredibly subtle signals. They would be absolutely thrilled to observe Hawking radiation from a microscopic black hole because it would represent one of the most significant discoveries in physics history. Direct experimental evidence for a phenomenon that has only been theorized about for decades. The detection of Hawking radiation would simultaneously confirm multiple aspects of theoretical physics. It would prove that black holes can evaporate, validate Hawking's calculations, potentially provide evidence for extra dimensions if the black hole formation occurred at LHC energies, and offer insights into the quantum nature of gravity. Scientists at CERN would be ecstatic to see such a signal, but they haven't, despite billions upon billions of particle collisions over more than a decade of operation. The Large Hadron Collider has never detected anything resembling Hawking radiation from a microscopic black hole. The absence of this signal is itself informative. It suggests either that the LHC isn't energetic enough to create black holes, or that extra dimensions don't exist in the way some theories predict, or both. Now, let's consider a more troubling scenario. What if we're wrong about Hawking radiation? After all, despite the theoretical elegance of Hawking's calculations, his radiation has never been directly observed coming from an actual black hole. The wavelength of Hawking radiation from a stellar mass or larger black hole would be comparable to the size of the event horizon itself, which means you'd need a detector larger than the black hole to observe it. That's obviously not practical. There is some indirect evidence supporting Hawking's theory. Scientists have created what they call analog black holes, in laboratory setting systems that don't involve actual gravitational black holes, but that mimic their mathematical properties. Some experiments with sonic black holes in fluids have observed phenomena consistent with Hawking radiation. But these are analogs, not the real thing. And while they're suggestive, they're not definitive proof. Additionally, some physicists have speculated that at microscopic scales, quantum effects might stabilize black holes, rather than causing them to evaporate. There are theoretical frameworks in which very small black holes could be metastable, not permanent, but not immediately evaporating either. They might stick around for some period of time before eventually dissipating. So let's entertain this possibility. Let's assume that Hawking radiation doesn't work the way we think it does, or doesn't apply to microscopic black holes, or is somehow suppressed in these extreme conditions. Would a black hole created by the LHC then proceed to devour our planet, growing larger as it consumed matter until it had swallowed everything? The answer is still no, and here's why. Black holes, contrary to their popular portrayal in science fiction and media, are not cosmic vacuum cleaners that suck up everything around them. Their event horizons are inescapable. True, once you cross that boundary, you can never get back out, but you still have to actually cross the boundary in the first place. And at the scales we're discussing, there's far more pushing matter away from the black hole than pulling it in. Outside of the event horizon, a black hole behaves gravitationally exactly like any other object of the same mass. If you replace the sun with a black hole of equal mass right now, the Earth's orbit wouldn't change at all. We'd freeze to death from the lack of sunlight, obviously, but we wouldn't spiral into the black hole. The gravitational pull would be identical to what the sun exerts on us currently. This is a crucial point that's often misunderstood. The tremendous gravitational effects of black holes, the extreme curvature of space-time, the inescapable pull only manifest very close to the event horizon. Farther away, gravity diminishes according to the inverse square law, just like it does for stars, planets, or any other mass. Now think about the mass of a microscopic black hole created in the LHC. We're talking about a black hole with the mass equivalent of the energy in a collision, roughly the mass of a few protons at most. The gravitational pull of such a black hole would be absolutely minuscule. Gravity is actually an extraordinarily weak force, especially compared to the other fundamental forces of nature. The electromagnetic force, for instance, is roughly 10 to the power of 36 times stronger than gravity. That's a trillion times stronger. The reason gravity seems strong to us is that we're near a very massive object, the Earth, and we're experiencing the cumulative gravitational effect of all that mass pulling on us. But for an object with the mass of a few protons, the gravitational force it exerts would be negligible. You're not getting pulled into the coffee cup on your desk or the phone in your hand, despite the fact that they contain vastly more mass than a microscopic black hole would. You wouldn't get pulled into a black hole with the mass of a few protons either. In fact, other forces would completely dominate. Consider what happens with the objects around you right now. You're not sinking through your chair or falling through the floor, despite Earth's gravity pulling you downward with considerable force. Why not? Because the electromagnetic forces in the atoms of the chair and floor are repelling the atoms in your body, preventing you from passing through solid matter. The electromagnetic force is so much stronger than gravity at these scales that it easily overcomes the gravitational attraction. The same principle would apply to a microscopic black hole. Even if it somehow persisted instead of evaporating, it would interact with its surroundings primarily through electromagnetic forces, not gravity. And here's where things get particularly interesting. In 2024, Harvard professor Avi Loeb published a fascinating paper exploring what he called black hole atoms. His hypothesis starts with a simple observation. If a black hole formed from the collision of protons, it would presumably inherit the electric charge of those protons. Protons carry positive electric charge, so a black hole formed from them would also be positively charged. Now, in normal atoms, positively charged nuclei are surrounded by negatively charged electrons. The electromagnetic attraction between opposite charges holds the electrons in orbit around the nucleus, creating stable atomic structures. Loeb asked, could the same thing happen with a charged black hole? In his theoretical framework, a microscopic black hole with positive charge could attract an electron through electromagnetic force. The electron would orbit the black hole at a distance outside the event horizon, just as electrons orbit atomic nuclei in regular atoms. To everything else in the universe, this system would behave essentially like a very compact atom. It would have quantum states, energy levels, the ability to form bonds with other atoms, all the properties we associate with normal matter. Such a black hole atom wouldn't be particularly stable, Loeb calculated. The unique properties of having a black hole at its center would make it prone to interactions and decay. But while it existed, it would behave more like an exotic form of matter than like the all-consuming void we imagine when we think of black holes. You could, in principle, have a collection of black hole atoms forming molecules, or even solid matter. Imagine holding a pen made of black hole atoms in your hand, as casually as you'd hold any other object. It's a mind-bending concept, the kind of idea that makes you realize how strange the universe can be at its extremes. But it illustrates an important point. Even if CERN created a charged microscopic black hole, the electromagnetic forces would likely dominate its behavior, not gravity. The black hole could fall to the floor of the detector and simply sit there, held up by the same electromagnetic repulsion that keeps you from sinking through the floor. The electrons in the floor's atoms would repel the electrons orbiting the black hole. From a practical standpoint, it would be no different than any other tiny particle landing on a surface. But let's strip away even more safety margins. Let's imagine a scenario where we get rid of the black hole's charge somehow. Perhaps it forms from a collision that results in a neutral particle, or perhaps it attracts particles of opposite charge until it becomes electrically neutral. Now we have a black hole with no electromagnetic properties, just pure gravity. Would such a black hole devour the planet? Once again, the answer is no, though for different and rather surprising reasons. Without electric charge, a microscopic black hole wouldn't be repelled by the electromagnetic forces in matter. There would be nothing to push against it, no force to hold it up against Earth's gravity, and so the black hole would simply fall. It would drop through the floor of the detector, through the bedrock beneath CERN, through the mantle of the Earth, accelerating as it fell toward the planet's center of mass. But here's what makes this scenario bizarre. The black hole would fall right through solid matter without being significantly slowed down. It would pass through rock, metal, magma, as if they weren't even there. It would fall all the way to Earth's core, then continue through to the other side of the planet, emerging somewhere in the Pacific Ocean before falling back down again, oscillating back and forth through the Earth like a pendulum. Why would this happen? The answer relates to the structure of atoms and the nature of matter itself. Atoms are mostly empty space, a fact that's hard to reconcile with our everyday experience of solid matter. But it's absolutely true. The nucleus of an atom contains more than 99.9% of the atom's mass, but it occupies only about 1/4 of the atom's volume. To visualize this, imagine the nucleus as a marble placed at the center of a large sports stadium. The electrons would be tiny specks orbiting somewhere in the stands, at the outer walls of the stadium. Everything in between the field, the seats, the airspace represents the empty space within the atom. And yet, when atoms come together to form solid matter, it feels solid to us because of the electromagnetic forces between atoms, not because the atoms themselves are packed tightly together. Particles that don't interact electromagnetically can pass through this empty space without hindrance. Neutrinos, for instance, are neutral particles produced copiously by the sun and other stars. About 100 trillion neutrinos pass through your body every single second. You don't feel them. They don't harm you. They pass through you, through the Earth, through everything, as if matter were almost completely transparent. Why? Because neutrinos have no electric charge. and interact only through the weak nuclear force and gravity, both of which are extremely weak at particle scales. The odds of a neutrino actually hitting an atomic nucleus as it passes through your body are minuscule. Over your entire lifetime, the probability that even a single neutrino will directly collide with one of the atoms in your body is only about 1 in 4. And that's with 100 trillion neutrinos passing through you every second for 70 or 80 years. A microscopic black hole without charge would behave similarly. It would pass through the spaces between atoms, rarely if ever actually encountering an atomic nucleus head-on. The vast majority of its journey through the Earth would involve passing through empty space, at least from the perspective of atomic structure. Now, it is theoretically possible that the black hole would occasionally get lucky and pass close enough to an atomic nucleus to capture it within its tiny event horizon. Each such encounter would add a minuscule amount of mass to the black hole, very slightly increasing its gravitational pull and making subsequent captures marginally more likely. So yes, in principle, a microscopic black hole falling through the Earth could accumulate mass over time. If it persisted long enough and got extraordinarily lucky with its encounters, it might gradually grow larger. But let's run the numbers on how likely this actually is. Consider the density of matter in the Earth. On average, the Earth has a density of about 5.5 grams per cubic centimeter. That sounds pretty dense, more than 5 times denser than water. But remember, matter is mostly empty space. The actual amount of solid material in that cubic centimeter, in terms of atomic nuclei that a chargeless particle could actually hit, is vastly smaller. The cross-sectional area of an atomic nucleus is roughly 10 to the power of minus 24 square centimeters. The cross-sectional area of a microscopic black hole with the mass of a few protons would be even smaller. Its event horizon would be far tinier than a nucleus. For such a black hole to capture material, it would need to pass within a distance of its event horizon to an atomic nucleus. The probability of this happening in any given pass through the Earth is astronomically small. Let's make a comparison. A neutrino, as I mentioned, has roughly a 1 in 4 chance of interacting with an atom in your body over an entire human lifetime. Your body contains approximately 7 times 10 to the power of 27 atoms. A neutrino passes through all of those atoms over and over again throughout your life, and still only has a 25% chance of ever hitting one. A microscopic black hole's event horizon would be far smaller than the interaction cross-section of a neutrino. Its chances of actually capturing a nucleus on any given pass through the Earth would be proportionally smaller. Even if it oscillated through the Earth billions of times, which it might do over millions or billions of years, it would be unlikely to accumulate any appreciable mass. Meanwhile, the Earth has a finite lifespan. In about 5 billion years, the Sun will exhaust its hydrogen fuel and begin fusing helium in its core. This will cause the Sun to expand into a red giant, its outer layers potentially reaching as far as Earth's current orbit. Even if our planet somehow survived the Sun's expansion, its surface would be rendered utterly uninhabitable, with temperatures high enough to vaporize rock. The point is this: even in this extremely pessimistic scenario, where we've assumed away Hawking radiation, extra dimensions, electric charge, and every other safety mechanism, a microscopic black hole created by the LHC would be highly unlikely to accumulate enough mass to pose any danger before the Earth meets its natural end, billions of years from now. But there's one final nail in the coffin of the CERN will destroy the world theory, and it's perhaps the most compelling argument of all. It comes from cosmic rays, high-energy particles that constantly bombard Earth from space. Cosmic rays are created by various astrophysical processes. Some come from the Sun, others from supernova explosions, still others from even more exotic sources, like pulsars, black holes, and active galactic nuclei. These particles, mostly protons, but also atomic nuclei and other subatomic particles, travel through space at tremendous velocities. Some of them eventually intersect with Earth's path around the Sunday. When cosmic ray particles strike Earth's atmosphere, they collide with atoms in the air, nitrogen, oxygen, and other atmospheric components. These collisions occur at very high energies. While most cosmic rays are relatively low energy, some carry truly astounding amounts of energy, far exceeding anything the Large Hadron Collider can produce. The highest energy cosmic ray ever detected, observed in 1991, and nicknamed the "Oh my God" particle, carried an energy of about 3 times 10 to the power of 20 electron volts. That's roughly 50 joules, about the energy of a baseball thrown at 60 miles per hour but compressed into a single subatomic particle. In comparison, the LHC's collision energies of 13.6 TeV are equivalent to about 2 × 10 to the power of -6 joules. The oh my god particle carried about 25 million times more energy than an LHC collision. And while such extreme cosmic rays are rare, more moderate, high-energy cosmic rays strike Earth's atmosphere constantly. Particles with energies comparable to or exceeding LHC collision energies hit our atmosphere thousands of times per day. This has been happening throughout Earth's entire history, more than 4.5 billion years. Here's the critical insight. If particle collisions at LHC energies could create dangerous black holes, then cosmic rays would have been creating them constantly throughout Earth's history. The planet would have been peppered with microscopic black holes for billions of years. If such black holes could accumulate mass and grow to threatening sizes, surely at least one would have done so by now. But Earth is still here. We haven't been consumed from within by growing black holes seeded by cosmic ray interactions. The Moon is still in orbit. Mars and Venus show no signs of having been devoured by black holes. The same goes for the countless asteroids, moons, and planets throughout the solar system and beyond, all of which are bombarded by cosmic rays, just as Earth is. The continued existence of Earth and other celestial bodies provides powerful empirical evidence that LHC energy particle collisions don't create dangerous black holes. The universe has been conducting this experiment on a vastly larger scale for billions of years, and nothing catastrophic has happened. Some might argue that collisions in particle accelerators are somehow fundamentally different from cosmic ray collisions. Perhaps the fact that particles in the LHC are colliding head-on, with both particles traveling at nearly light speed in opposite directions, creates conditions that don't occur in nature. After all, cosmic ray collisions typically involve a fast-moving particle striking a stationary target atom, but physicists have analyzed this scenario carefully, considering the kinematics from different reference frames. In the frame of reference moving with one of the particles, a head-on collision in the LHC looks exactly like a cosmic ray collision. The physics is identical. If one scenario could produce dangerous black holes, so could the other. Moreover, even if accelerator collisions somehow were unique, we wouldn't need to rely solely on cosmic ray evidence from Earth. High-energy cosmic rays also strike dense stellar remnants like white dwarfs and neutron stars, objects much denser than Earth where any created black hole would have an easier time accumulating mass. If dangerous black holes could be created and could grow, these dense objects would be prime targets. Yet white dwarfs and neutron stars exist in abundance throughout the universe, apparently unaffected by any such process. The cosmic ray argument effectively closes the case. Not only do our theoretical models suggest that the LHC can't create dangerous black holes, but we also have billions of years of empirical evidence from natural processes occurring throughout the universe. CERN isn't doing anything that nature hasn't been doing constantly since the formation of the solar system. So there you have it. If we're living in a universe with extra dimensions, which is far from proven, and if those extra dimensions lower the Planck energy enough that the LHC can create black holes a big if, and if Hawking radiation doesn't work or is somehow suppressed another unlikely scenario, and if those black holes have no electric charge, stripping away another safety mechanism, and if such a black hole somehow got extraordinarily lucky in accumulating mass, despite the emptiness of matter at atomic scales, an astronomical improbability, then, yes, technically, the Large Hadron Collider could create a black hole that would eventually consume the Earth from within, slowly eating away at our planet's core until the crust collapsed and everything fell into a void beneath our feet. But every single one of those conditions would need to be true simultaneously, and each one is highly improbable on its own. The compound probability of all these unlikely scenarios occurring together is so close to zero that it's not meaningfully different from impossible. In truth, there have been times throughout the history of science when researchers have taken genuine risks with their experiments, times when the pursuit of knowledge outpaced our understanding of the potential consequences. These moments serve as cautionary tales, reminding us that scientific inquiry, for all its benefits, must be tempered with careful consideration of safety and ethics. Consider the Manhattan Project during World War II. Before the first atomic bomb test, codenamed Trinity, some physicists expressed concern about a truly terrifying possibility that the intense heat and pressure of a nuclear explosion might ignite the Earth's atmosphere. The theory was that the extreme conditions could trigger a fusion reaction in atmospheric nitrogen, creating a self-sustaining chain reaction that would spread across the globe, turning our entire atmosphere into a stellar-scale fusion furnace. This wasn't idle speculation from outsiders. It was a concern raised by physicists working on the project itself, people who understood the mathematics and physics involved. Edward Teller, one of the key figures in developing thermonuclear weapons, had initially raised the possibility, while subsequent calculations by Hans Bethe and others concluded that atmospheric ignition was impossible. The conditions required for nitrogen fusion were far more extreme than a nuclear explosion could produce. The fact that such a scenario was even considered seriously shows how scientists were venturing into truly unknown territory. They proceeded with the test because the mathematics indicated it was safe, but there was an element of uncertainty, of venturing into genuinely uncharted waters. As it turned out, the calculations were correct. The atmosphere didn't ignite, and nuclear weapons, while devastating, operate within predictable physical limits. But the scientists involved had to confront the possibility, however remote, that their experiment might trigger an extinction-level catastrophe, or consider early experiments with recombinant DNA in the 1970 seconds. Scientists had just developed the ability to cut and splice genetic material, to take genes from one organism and insert them into another. This was revolutionary technology with enormous potential for medicine, agriculture, and basic research. But it also raised alarming questions. What if scientists accidentally created a dangerous pathogen? What if modified bacteria escaped the laboratory and spread into the environment? These concerns led to the Asilomar Conference in 1975, where molecular biologists gathered to establish safety guidelines for genetic engineering research. They voluntarily imposed restrictions on their own work until the risks could be better understood. Some experiments were deemed too dangerous to perform at all. Others could only be conducted under stringent containment conditions. This self-imposed moratorium on certain types of research was unprecedented, a recognition that scientific advancement needed to be balanced against potential risks to public health and safety. The field of synthetic biology raises similar questions today. As scientists gain the ability to design organisms from scratch, to write genetic code as if programming a computer, we enter territory that previous generations could barely imagine. What are the risks of creating synthetic life forms? Could they escape into the environment? Could synthetic biology techniques be misused to create biological weapons? These are not hypothetical concerns. They're active debates within the scientific community, informing decisions about research directions and safety protocols. Medical research, too, has its dark history of reckless experimentation. The infamous Tuskegee syphilis study, which ran from 1932 to 1972, deliberately withheld treatment from African American men with syphilis to study the disease's progression, even after penicillin became available as an effective cure. Participants were lied to, told they were receiving treatment when they weren't, and the study continued for decades despite causing immense suffering and preventable deaths. This wasn't scientists taking risks with unknown phenomena, it was conscious disregard for human welfare in the name of research data. Or consider the history of radiation experiments. In the early days of X-ray technology and radioactive materials, before the dangers were fully understood, researchers exposed themselves and others to dangerous levels of radiation. Some of these exposures were accidents, the result of ignorance about radiation's biological effects. But others were more problematic government-sponsored radiation experiments on prisoners, hospital patients, and other vulnerable populations, often without informed consent, conducted to study radiation's effects on human health. These examples share a common thread. They represent cases where the pursuit of scientific knowledge either risked catastrophic consequences or caused actual harm, whether through recklessness, inadequate safety measures, or deliberate disregard for ethical principles. They remind us that scientists, despite their expertise and generally good intentions, are not infallible. They can make mistakes in judgment. They can underestimate risks. They can prioritize advancement of knowledge over other important considerations. This is why we've developed elaborate systems of ethics review, safety protocols, and regulatory oversight for scientific research. It's why experiments involving human subjects must now be approved by institutional review boards. It's why research with dangerous pathogens is conducted in high-containment laboratories with strict protocols. It's why environmental impact assessments are required before deploying new technologies into ecosystems. So when evaluating CERN and the Large Hadron Collider, it's entirely appropriate to ask, is this another case of scientists taking unacceptable risks? Are they being reckless with the planet's safety in their eagerness to probe the fundamental structure of matter? Should we be concerned that they've acknowledged a non-zero probability of creating black holes? But hopefully, after examining the evidence, you can see that the Large Hadron Collider doesn't fall into the category of dangerous, reckless experimentation. The risks, such as they are, have been analyzed exhaustively. Multiple independent safety assessments have been conducted, involving physicists from around the world, not just those working at CERN. These assessments have consistently concluded that the LHC poses no danger. The theoretical scenarios under which the LHC could create dangerous black holes require multiple, highly improbable conditions to be true simultaneously. We'd need extra dimensions to exist with very specific properties. We'd need Hawking radiation to not work as predicted. We'd need the created black holes to be uncharged and stable. We'd need them to successfully accumulate mass despite the near emptiness of matter at atomic scales. Every one of these conditions is unlikely. All of them occurring together is vanishingly improbable. More importantly, we have empirical evidence from nature itself. Cosmic rays have been conducting experiments equivalent to the LHC's collisions for billions of years, bombarding Earth and countless other celestial bodies throughout the universe. If such collisions could produce dangerous black holes, we'd expect to see evidence of it. We don't. The continued existence of planets, stars, and other astronomical objects provides powerful testimony that these processes are safe. The scientists at CERN aren't cavalier about safety. They've thought carefully about the risks, engaged with critics, published detailed safety analyses, and addressed concerns raised by the public and other physicists. When they say the LHC is safe, that conclusion isn't based on blind faith or wishful thinking. It's grounded in solid physics and supported by observational evidence from the universe around us. So no, CERN and the Large Hadron Collider do not represent a case of scientists recklessly gambling with humanity's future. The odds of the LHC creating a dangerous black hole are so low that we can confidently say we're not at any real risk from their experiments. The probability isn't precisely zero. Very few things in science are absolute, but it's close enough to zero that we need not lose sleep over it. But let's step back from the black hole question and consider the broader picture. The Large Hadron Collider and facilities like it represent something profound about the human species, our drive to understand the universe we inhabit. This drive has been with us throughout our history, manifesting in different ways across cultures and eras, but always present. Always pushing us to ask deeper questions. Ancient peoples looked up at the night sky and wondered about the nature of the stars. They noticed patterns, the regular motions of celestial objects, and sought explanations. They developed cosmologies, creation myths, models of the universe that attempted to make sense of what they observed. These early efforts weren't scientific in the modern sense. They mixed observation with mythology, physics with philosophy, often in ways that seem naive to us now, but they represented the same fundamental impulse, the desire to understand. As civilizations developed more sophisticated tools and methods, their understanding deepened. The ancient Greeks developed geometry and used it to estimate the size of the Earth and the distance to the Moon. Chinese astronomers maintained detailed records of celestial phenomena for centuries, noting comets, supernovae, and planetary motions with remarkable precision. Islamic scholars preserved and extended Greek astronomical knowledge during the medieval period, making observations and calculations that would later influence European science. The scientific revolution of the 16th and 17th centuries marked a turning point. Figures like Copernicus, Galileo, Kepler, and Newton developed mathematical frameworks that could accurately predict planetary motions and other natural phenomena. For the first time, humans had theories that could make precise, testable predictions about the physical world. These theories could be confirmed or refuted through observation and experiment. Science began to diverge from philosophy, becoming its own discipline with its own methods and standards of evidence. Each generation of scientists built on the work of their predecessors, developing more sophisticated theories and more powerful instruments. Spectroscopy revealed the chemical composition of distant stars. Einstein's theories of relativity showed that space and time were not the fixed, absolute entities Newton had imagined, but were dynamic, and interrelated. Quantum mechanics revealed the strange probabilistic nature of reality at atomic scales. Throughout the 20th century, physicists worked to understand the fundamental constituents of matter. They discovered that atoms, once thought to be indivisible, were actually composed of smaller particles, electrons orbiting a nucleus of protons and neutrons. Then they discovered that protons and neutrons themselves were composed of even smaller particles called quarks, held together by particles called gluons through the strong nuclear force. Gradually, a picture emerged: the Standard Model of particle physics, a comprehensive theory describing all known fundamental particles and 3 of the 4 fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. Gravity remains separate, not yet successfully integrated into the quantum framework. The Standard Model has been extraordinarily successful, making predictions that have been confirmed by experiments over and over again. But the Standard Model, despite its success, is clearly incomplete. It doesn't explain gravity. It doesn't explain dark matter or dark energy. It doesn't explain why the universe contains more matter than antimatter. It doesn't explain why particles have the masses they do, or why there are 3 generations of matter particles when one would seem sufficient. It raises as many questions as it answers. This is where facilities like the Large Hadron Collider come in. They allow us to probe nature at higher energies, shorter distance scales, more extreme conditions than we can access any other way. They let us test the predictions of our theories in new regimes and search for phenomena that might point toward physics beyond the Standard Model. The discovery of the Higgs boson in 2012 exemplifies this process. The Higgs was predicted to exist by the Standard Model, but for nearly 50 years it remained undetected. Its mass was unknown, and while theorists could estimate roughly where it should be, confirmation required direct observation. The LHC was designed, in part, to find the Higgs, and it succeeded. This wasn't just a matter of confirming what we already believed, it was testing whether our theoretical framework accurately described reality. If the Higgs hadn't been found, or if it had properties different from predictions, that would have indicated serious problems with the Standard Model. Now, physicists are using the LHC to search for other phenomena. They're looking for evidence of supersymmetry, a theoretical framework that predicts each known particle has a heavier superpartner. They're searching for dark matter candidates, particles that might make up the invisible mass that dominates the universe. They're studying the properties of exotic particles and looking for any deviations from Standard Model predictions that might hint at new physics. This research is fundamentally important, even if its practical applications aren't immediately obvious. Understanding the basic structure of reality, the fundamental laws that govern matter and energy, is valuable in its own right. It's part of humanity's long quest to comprehend the universe we find ourselves in. And while basic research often seems disconnected from everyday concerns, history shows that today's esoteric discoveries often become tomorrow's transformative technologies. Consider quantum mechanics. In the 1,920 seconds and 1,930 seconds, when physicists were working out the strange rules governing atomic and subatomic particles, this seemed like the most abstract, impractical research imaginable. The phenomena they were studying occurred at scales far removed from human experience. Yet quantum mechanics underlies much of modern technology. Semiconductors, which make possible all electronic devices from smartphones to supercomputers, work because of quantum mechanical properties of materials. Lasers, MRI machines, atomic clocks, quantum cryptography all depend on quantum effects. Or consider general relativity. Einstein's theory of gravity seemed like pure theory when he published it in 1915, with few practical applications beyond explaining some subtle astronomical observations. Today, GPS satellites must account for relativistic effects, both the time dilation due to their velocity and the time dilation due to Earth's gravitational field, to maintain accurate positioning. Without corrections based on general relativity, GPS would accumulate errors of several kilometers per day. We can't predict what technologies might emerge from our current fundamental research. Perhaps understanding the Higgs mechanism will lead to new insights about mass and inertia that enable revolutionary propulsion systems. Perhaps discovering dark matter's nature will open up entirely new fields of technology. Perhaps exploring physics at high energies will reveal phenomena we can't currently imagine. Or perhaps the discoveries will remain purely scientific, expanding our knowledge without immediate practical application. Either outcome is valuable. The pursuit of understanding for its own sake is a worthy human endeavor, one of the things that distinguishes us as a species. We're not content to simply exist. We want to know why we exist, how the universe works, what the fundamental nature of reality is. This curiosity has driven our species' greatest achievements. And there's something inspiring about the scale of ambition represented by projects like the Large Hadron Collider. Thousands of scientists and engineers from around the world, collaborating across national boundaries, pooling their knowledge and resources to build a machine that can probe the structure of matter at the deepest level we've ever achieved. The LHC represents humanity at its best. Cooperative, curious, ambitious, reaching beyond our immediate needs to pursue knowledge. The facility itself is a marvel of engineering. Consider the challenge of accelerating particles to 99,999,999,1%, the speed of light. At these velocities, relativistic effects become crucial. The protons circling the LHC have a mass about 7,500 times greater than their rest mass due to their kinetic energy. They circle the 27-kilometer ring more than 11,000 times per second. Keeping these beams stable and focused requires exquisite precision. The magnets that guide the particle beams must be superconducting, cooled to temperatures colder than outer space, about 1.9 degrees above absolute zero, colder than the cosmic microwave background radiation that fills the universe. This requires a sophisticated cryogenic system using liquid helium. The vacuum inside the beam pipes must be as empty as possible, approaching the vacuum of interstellar space. To prevent collisions with stray molecules that would disrupt the beam, the detectors surrounding the collision points are equally impressive. The Atlas detector, one of the largest, is 46 meters long and weighs about 7,000 tons. It contains roughly 100 million electronic sensors to track the particles produced in each collision. The CMS detector, though more compact, is even heavier at 14,000 tons. These detectors must precisely measure the properties of particles that exist for only billionths of a second, reconstructing their trajectories and energies from the tiny signals they leave behind. The computing infrastructure required to process the data is staggering. The LHC generates about 1 billion particle collisions per second. Only a tiny fraction of these, perhaps a few hundred per second, are interesting enough to record. But even these selected events produce enormous amounts of data. The LHC generates roughly 30 petabytes of data per year. That's 30 million gigabytes, enough to fill millions of DVDs. Processing this data requires a distributed computing network spanning hundreds of institutions across the globe. All of this, the engineering, the international collaboration, the scientific ambition, serves the goal of understanding nature at its most fundamental level. And while the research might seem abstract and removed from everyday concerns, it's addressing questions that humans have wondered about for millennia. What is everything made of? How did the universe begin? What are the basic laws that govern all physical phenomena? These aren't idle questions. They're deeply connected to our place in the cosmos, to how we understand ourselves and our world. Every advance in fundamental physics changes, in subtle but important ways, our conception of reality. We've learned that matter is mostly empty space, that particles behave in probabilistic ways, that space and time are intertwined and flexible, that the universe began in a hot, dense state and has been expanding for nearly 14 billion years. Each of these insights changed how we think about existence itself. The Large Hadron Collider continues this tradition of expanding human understanding. Every collision, every measurement, every analysis contributes to our growing body of knowledge about the fundamental nature of reality. And while we haven't yet found evidence of supersymmetry, or detected dark matter particles, or discovered extra dimensions, the search itself is valuable. Negative results finding that certain theories don't match reality are just as scientifically important as positive discoveries. They narrow the range of possibilities, ruling out incorrect ideas and guiding us toward better theories. The absence of certain predicted particles at the energies the LHC can reach tells us something important. If those particles exist, they must be heavier than we thought, or interact more weakly with ordinary matter, or have properties different from our current models predict. This information shapes the next generation of theories and experiments. Science advances through this iterative process of prediction, testing, refinement, and CERN is already looking ahead to what comes after the Large Hadron Collider. The proposed Future Circular Collider, with its 91-kilometer circumference and collision energies approaching 100 TeV, would probe nature at even smaller distance scales, higher energy regimes. Such a facility would cost tens of billions of dollars and take decades to build, requiring international cooperation on an even larger scale than the LHC. Is such an investment worthwhile? Different people will answer that question differently, depending on how they value fundamental research versus other priorities. There are certainly urgent problems facing humanity: climate change, poverty, disease, conflict that demand resources and attention. Some argue that spending billions on particle physics is a luxury we can't afford when so many pressing needs remain unmet. Others counter that the budget for fundamental physics research is actually quite small compared to overall government spending, and that advancing human knowledge shouldn't be viewed as competing with other goals, but rather as part of a balanced approach to societal development. The United States federal budget, for instance, allocates roughly $1 billion per year to particle physics research, less than 0.02% of total spending. For comparison, military spending exceeds $800 billion annually. Even modest shifts in priorities could fund fundamental research without impacting other programs. Moreover, the economic benefits of scientific research often extend far beyond the immediate discoveries. CERN itself contributed to the development of the World Wide Web. Tim Berners-Lee invented it in 1989 while working at CERN to help physicists share information. The web has transformed global commerce, communication, and culture in ways that would have been impossible to predict, creating trillions of dollars in economic value. Who knows what future technologies might emerge from today's research? The medical imaging techniques used in PET scanners and certain types of radiation therapy were developed through particle physics research. The techniques used to accelerate particles for research are closely related to those used in particle therapy for treating cancer. Advances in detector, technology, computing, materials, science, and engineering driven by projects like the LHC have applications across numerous fields. But perhaps the strongest argument for continuing fundamental research isn't economic or technological, it's philosophical. Humans are curious beings. We want to understand our world, our universe, our place within the grand scheme of things. This desire for understanding is part of what makes us human. Throughout history, across all cultures, people have looked up at the stars and wondered about their nature. We've asked questions about the composition of matter, the nature of time, the origin of everything. Science is our most successful method for answering these questions. It provides a systematic way to investigate nature, to test ideas against reality, to build knowledge that's reliable and accurate. And while science has practical benefits, its deepest value might be existential. It helps us understand who and what we are. Consider what we've learned about our cosmic context through scientific investigation. We've discovered that Earth is not the center of the universe, but a planet orbiting an ordinary star. We've learned that our Sun is one of hundreds of billions of stars in a galaxy called the Milky Way, and that the Milky Way is one of hundreds of billions of galaxies in the observable universe. We've determined that the universe is approximately 13.8 billion years old, that it began in a hot, dense state and has been expanding ever since. We've learned that the atoms making up our bodies were forged in the nuclear furnaces of stars that lived and died before our sun was born. We're literally made of stardust, the carbon in our cells, the calcium in our bones, the iron in our blood, all created through nuclear fusion in stellar cores and scattered into space when those stars exploded as supernovae. We're part of the universe examining itself, matter organized in such a way that it can contemplate its own nature. These insights are profound. They place humanity in cosmic context, showing both our insignificance, we're tiny beings on a small planet, orbiting an average star in one galaxy among billions, and our significance, we're the universe, becoming conscious of itself, capable of understanding the laws that govern existence. This perspective can be humbling and inspiring simultaneously. The research conducted at facilities like CERN continues this tradition of expanding our cosmic perspective. By probing the fundamental structure of matter and energy, by testing theories about the basic laws of physics, by searching for dark matter and evidence of extra dimensions, physicists are addressing questions about the ultimate nature of reality. What is everything made of at the deepest level? Are there phenomena beyond what we currently understand? What happened in the first moments after the Big Bang? How will the universe evolve in the distant future? These questions might not have immediate practical applications, but they speak to something deep in the human spirit, our need to understand. to make sense of existence, to push the boundaries of knowledge, and in pursuing answers, we often discover unexpected truths that reshape our understanding in fundamental ways. Returning to the question of black holes and the LHC, we can now see it in broader context. The concern about CERN creating dangerous black holes arose from our expanding theoretical understanding of physics. As physicists developed models involving extra dimensions, speculative theories, attempting to unify all forces and explain various mysteries, they realized these models had implications for black hole formation. If extra dimensions existed with certain properties, the energy threshold for creating black holes might be lower than previously thought, potentially within reach of the LHC. Rather than ignore or downplay this possibility, CERN and the wider physics community addressed it directly. They conducted detailed safety assessments, examining the scenarios under which black holes might form, and analyzing what would happen if they did. They considered Hawking radiation, electromagnetic effects, gravitational capture cross-sections, all the factors that might influence whether a microscopic black hole could pose a danger. The conclusions were reassuring. Even in the unlikely event that the LHC created black holes, multiple independent mechanisms would prevent them from posing any threat. And beyond the theoretical arguments, the empirical evidence from cosmic rays provided strong support for safety. Nature has been conducting these experiments for billions of years on a vastly larger scale, with no catastrophic results. This represents science working as it should. Researchers identified a potential concern, analyzed it thoroughly, consulted widely, published their findings for scrutiny by the scientific community, and reached a consensus based on evidence and sound reasoning. The process was transparent, open to criticism, and responsive to public concern. This is very different from reckless experimentation or dismissing safety concerns out of hand. Some critics argued that scientists couldn't be trusted to evaluate the safety of their own experiments, that they had inherent conflicts of interest that would bias their conclusions. There's a legitimate concern here. People are often poor judges of risks associated with their own activities. But the safety assessments for the LHC weren't conducted solely by CERN staff. They involved independent physicists from institutions around the world, including many who had no direct involvement with the LHC. The arguments and calculations were published openly, available for anyone with the relevant expertise to examine and critique. Moreover, the scientists involved had no incentive to minimize real risks. They live on Earth too, along with their families and loved ones. They have as much stake in the planet's survival as anyone else. The stereotype of the mad scientist pursuing knowledge regardless of consequences doesn't match reality. Physicists are generally quite careful, even conservative, when it comes to safety considerations. The public debate about LHC safety, while sometimes sensationalized in media coverage, served a valuable purpose. It forced the scientific community to explain their reasoning clearly, to address concerns seriously, and to make their safety assessments publicly available. This kind of engagement between scientists and the broader public is healthy, even when it's uncomfortable for researchers who might prefer to work without public scrutiny. Science doesn't occur in a vacuum, isolated from society. Large-scale research facilities like CERN are funded by taxpayers, occupy public space, and affect the communities around them. The public has a legitimate interest in understanding what these facilities do and whether they pose any risks. Scientists have a responsibility to communicate clearly about their work, to listen to concerns, and to address them substantively. This is particularly important for research that pushes into genuinely new territory. When scientists are exploring phenomena that have never been studied before, there's inherent uncertainty. No matter how confident we are in our theoretical understanding, there's always the possibility of surprises. Nature has surprised us before, revealing phenomena we didn't predict. Maintaining some epistemic humility, acknowledging the limits of our knowledge, is appropriate. At the same time, we can't let theoretical possibilities, however remote, paralyze us. If we refuse to conduct any experiment with a non-zero probability of danger, we'd never make progress. Every activity carries some risk. Driving to the store, flying in an airplane, even walking downstairs all have measurable probabilities of injury or death. We accept these risks because they're small and because the benefits outweigh them. The risk from the LHC creating dangerous black holes, based on everything we know about physics and everything we've observed about the universe, is extraordinarily small, so small as to be effectively zero. It's certainly far smaller than countless risks we accept without a second thought in our daily lives. Worrying about the LHC while driving a car, for instance, represents a dramatic miscalibration of risk assessment. None of this means we should accept scientists' assurances uncritically or stop asking questions about safety. Healthy skepticism and continued vigilance are appropriate, but they should be proportionate to actual risks, grounded in understanding rather than fear, and responsive to evidence and logical argument. The saga of the Large Hadron Collider and the black hole controversy illustrates both the promise and the challenges of big science in the modern era. It shows how theoretical advances can raise unexpected concerns, how scientific communities can work to address those concerns, and how public engagement with science can be both beneficial and complicated. Looking forward, as CERN contemplates even larger and more energetic particle colliders, similar questions will arise. Each increase in collision energy brings us closer to the Planck scale, where our understanding becomes more speculative. While we're still extraordinarily far from reaching energies where black hole creation becomes plausible in standard physics, the gap narrows with each generation of accelerators. This means that future facilities will need to conduct similar safety assessments, examining any theoretical scenarios that might pose risks. The process will likely become more sophisticated as our understanding of high-energy physics improves. Perhaps we'll develop more complete theories that make clearer predictions about what happens at extreme energies. Perhaps we'll discover new phenomena that change how we think about these questions. What's certain is that humanity's quest to understand the fundamental nature of reality will continue. We're driven by curiosity, by a desire to know how the universe works at its deepest level. Facilities like the Large Hadron Collider are tools in this quest, powerful instruments that let us probe nature in ways previous generations could only dream of. The concerns about black hole creation, while ultimately unfounded, remind us that this quest isn't without considerations. We must balance our desire for knowledge with careful attention to safety, proceed with appropriate caution when venturing into new regimes, and maintain clear communication with the broader public about what we're doing and why. But we shouldn't let unfounded fears stop us from exploring. The universe is vast and strange and full of wonders we've barely begun to understand. Black holes are real phenomena, fascinating objects that challenge our comprehension of space and time. We should study them, learn about them, probe their properties and behavior. But we needn't fear that particle physics experiments will create dangerous ones here on Earth. So I think we can confidently say that we're not at any real risk from CERN's experiments. The Large Hadron Collider will continue to collide particles at tremendous energies, searching for new physics, testing theoretical predictions, and expanding human knowledge. It will do so safely, without creating black holes that devour the planet. Of course, there's always that one other possibility we mentioned: the portal to hell. Despite thorough fact-checking and scientific debunking, that particular conspiracy theory refuses to die. Perhaps we should remain vigilant, just in case. Maybe CERN's next discovery won't be a new particle or evidence for extra dimensions, but rather an actual gateway to infernal realms. One never knows what might emerge from the cutting edge of physics research. But in all seriousness, the Large Hadron Collider represents humanity at its best: curious, ambitious, collaborative, reaching beyond our immediate needs to pursue deeper understanding. It's a monument to human ingenuity and our species' drive to comprehend the cosmos we inhabit. And while it won't create dangerous black holes, it will continue to illuminate the fundamental nature of reality, one collision at a time. The universe is strange and beautiful and full of mysteries. We're privileged to live in an era where we can probe those mysteries with unprecedented precision, where we can test theories about the first moments after the Big Bang, where we can search for the invisible matter that makes up most of the universe's mass. The Large Hadron Collider is one of our most powerful tools for this exploration. As we look up at the night sky, as humans have done for thousands of generations, we can appreciate how far we've come in understanding what we're looking at. Those points of light are distant suns, many with their own planets. The hazy band of the Milky Way is our galaxy seen from within. Hundreds of billions of stars. The faint smudges visible through telescopes are other galaxies, island universes containing billions of stars of their own, scattered across vast cosmic distances. We know these things because of science, because of careful observation and measurement and theoretical work and experimental testing. We know them because researchers have dedicated their lives to pushing the boundaries of human knowledge, to asking difficult questions and seeking rigorous answers. The Large Hadron Collider is part of this grand tradition. It's asking questions about the smallest scales of existence, probing the quantum realm where particles pop in and out of existence, where uncertainty is fundamental, where the rules that govern everyday objects break down and stranger principles take hold. And while we can't predict what future generations will discover, what technologies they'll develop, what new understanding they'll achieve, we can be certain that they'll build on the work being done today. The research conducted at CERN now will inform physics for decades to come, shaping the questions researchers ask and the theories they develop. Perhaps those future physicists will finally crack the code of quantum gravity, successfully merging quantum mechanics with general relativity into a single coherent framework. Perhaps they'll discover what dark matter is made of, solving one of cosmology's greatest mysteries. Perhaps they'll find evidence for extra dimensions or supersymmetry, or something entirely unexpected that changes how we think about reality. Or perhaps the answers to these questions lie beyond what particle accelerators can reveal, requiring different approaches or technologies we haven't yet imagined. Perhaps we'll need to look to the cosmos itself, studying black holes and neutron stars and the cosmic microwave background, or conduct experiments that don't involve smashing particles together, but rather manipulating quantum states in subtle ways. Whatever the path forward, the pursuit will continue. Humans will keep asking questions, keep seeking understanding, keep pushing the boundaries of knowledge. It's what we do. It's part of our nature as a species. And facilities like the Large Hadron Collider, for all the concerns they've raised and the headlines they've generated, are really just the latest chapter in a story that began when our ancestors first looked up at the stars and wondered what they were seeing. So the next time you read a headline about CERN creating black holes or opening portals to other dimensions, you can smile knowingly. You understand the physics now. You know about Schwarzschild radii and Planck energy, about Hawking radiation and electromagnetic forces, about cosmic rays and the emptiness of matter at atomic scales. You know why the fears are unfounded, even if they make for exciting headlines. And you can appreciate the remarkable human achievement that the Large Hadron Collider represents. Thousands of scientists collaborating across borders, using mathematics and physics to probe the fundamental nature of matter and energy, building machines of extraordinary precision and power, all in service of expanding human understanding of the universe we call home. The universe is vast beyond comprehension, ancient beyond our ability to truly grasp. We're tiny beings on a small planet, existing for a brief moment in cosmic time. But we're also something remarkable. We're matter organized in such a way that it can understand itself. Intelligence emerged from the quantum dance of particles and forces. We can look out at the cosmos and comprehend what we're seeing. We can probe the nature of reality itself and understand the answers we find. That's worth celebrating. That's worth supporting. And it's definitely worth the non-existent risk of creating a planet-devouring black hole. After all, we're still here. The Earth continues to spin, and human knowledge continues to expand, one particle collision at a time. The cosmos awaits our continued exploration, full of questions still unanswered and mysteries still unsolved. The Large Hadron Collider is helping us explore those mysteries, safely and successfully, despite what the more sensational headlines might suggest. And that's something we can all appreciate, even if we don't fully understand the mathematics involved or the exotic theories being tested. Science continues its march forward, driven by human curiosity and enabled by remarkable technology. The fears about CERN destroying the world will likely persist in some corners of the internet, immune to evidence or logic. But for those willing to look at the actual science, the conclusion is clear. We're safe, the research is valuable, and the pursuit of knowledge continues unabated. And if CERN ever does open that portal to hell, well, at least we'll have some advance warning from the conspiracy theorists. They'll have been predicting it all along.